Welcome. Today I'm going to talk to you guys about our first topic for the second semester, and that is impulse. It's going to lead us into a topic that I think you'll find to be exciting and fun with the application of a lot of the things we learned in the first semester, and that's called momentum. Momentum is really about the study of how things collide and how things explode. Two things that I know high school students tend to love. And so we're going to go ahead and talk about that. But before we do it, we have to revisit a couple of topics from last semester that we're going to try to morph into something that can be more useful for this semester. And so as you can see here, I've written the formula 4.2 at the top there. That's Newton's second law, right? So just a helpful reminder, that's Newton's second. Don't forget. And it says that the net force right here is equal to the mass times the acceleration that it produces. Don't forget that this is a net force. I didn't write it in there, but you want to make sure to remember that because you have to take that into account when you are thinking about how things are actually moving, right? So if you're talking about a collision and you're talking about the force that something applies to something else, you're going to have to take into account the fact that it's really the net force that does the changes in motion. And so I'm going to go ahead and make sure to write that down there. Net force right there. There we go. Don't forget that. Now, F equals ma in my mind is not the most useful format for this particular formula because I think a lot of people don't have the idea of what really acceleration is firmly planted in their head. We know what it means to move. We know what it means to speed up, and we know what it means to slow down. But in a numerical sense, we have a much better understanding of velocity than we do acceleration. And so what we want to do here first, before we do anything else, is we want to combine up these two formulas right here. So formula 4.2 is F equals ma. That's the Newton's second law, as we said. And then formula 2.3 is the acceleration equals the change in velocity over the change in time. Don't forget that acceleration and velocity are vectors, and I've indicated that by making them bold and not italics. Whereas time is not a vector, and so therefore it's in italics and not bold. So anyway, if I go ahead and combine these two formulas, you can see I've got an A here and I've got an A there, and so I can plug in all of this stuff into this space. And so I go ahead and write that out, and it looks like this. Now this is not one of our formulas, so you're not going to see it on the formula sheet. Don't worry about it. We're going to morph it one more time into something a little bit more useful. It's not going to look useful, because in math class you were so used to getting one variable over on the other side that you sometimes when you see two variables on a side you kind of get, I don't know, kind of nervous about it, or you think that there's something else that you still need to do. And in this case, we're going to morph it into this right here. And this is actually your first formula for the second semester. It's F delta T equals M delta V. It doesn't look like it's simplified, but it is simplified as far as we want to go with it for this unit. So let's take a look at what this actually says. This says the net force that is applied for a certain period of time will change the velocity of a given mass. Okay, so I'm going to say it again. The net force here, applied for a certain time, will change the velocity to a certain amount when applied to a given mass. That's what that really says. And so, again, I think that's an easier way to think about Newton's second law. In actuality, it is Newton's second law. It's just sort of changed a little bit. So it's not really its own formula, even though I've made it such. Now, I'm going to break out just this part for this video right here. Oops, there we go. That part. And I'm going to call that a special thing, and I'm going to call that impulse. Boy, my pen is not cooperating today here. Impulse. So impulse is kind of a special thing. It's a way to kind of keep track of how things are behaving. So it doesn't really, typically, we don't talk about it in real life because there's no real easy gut feeling that you get from impulse. It is the amount of force that you apply over a certain period of time. So I want you to think about what that means for a second here. If I apply a small force over a small period of time, I end up with a small impulse. And you can assume that these are vectors right there. However, if I instead apply a large force over a small period of time, I end up with a much larger impulse. And finally, if I apply a small force over a very large period of time, I can also end up with a large impulse. And so you notice that there are actually two ways to get a large impulse. You can either use a large force, or you can apply it for a large period of time. And so this impulse idea is kind of a, I don't know, it's kind of a tricky one because it's not something that has any real description in real life. But it is something that you use. And so I want you to go ahead and take a look at this little Mini Coupe right here. You notice that it has three safety mechanisms here. It has seat belts, it has airbags, and it has crumple zones. All of these things are meant to protect you if you get into a car crash, which is a kind of a collision, right? And so how do they protect you? Do they change how much your velocity has to change? No. Do they change your mass at all? No. What they change, though, is they change this delta t right there. So they apply a larger impulse to you. In other words, they try to make you stop by trying to apply it a smaller force over a larger period of time. And so safety mechanisms all want to make the change in time as large as possible to try to increase the impulse. The worst case scenario would be a very small change in time. So in other words, you stopped very quickly. If you stop very quickly, look at the amount of force that has to be applied to stop you very quickly. It's much larger, and so therefore you're much more prone to injury. Therefore, if we can change that, if we can apply the same impulse but do it by applying a smaller force over a much larger period of time, then you're going to be a lot safer. And so a seatbelt stops you slower as you move forward. Airbags cushion your face over a larger period of time. Again, it's not a big period of time, but it's much larger than when you hit the steering wheel. And then the crumple zones are meant to collapse the entire car over a larger period of time. And so impulse is the same in your car crash, but you use a larger period of time to be able to make a smaller force and therefore keep people safer. That's how they work. Football helmets work the same way, and we'll talk a little bit more about football helmets later in the course here. One last thing, whenever you hear impulse, if you're a geek like me, you always think about Star Trek. And so I had to put in Star Trek's impulse engines right there. Those little engines right there on the USS Enterprise, what they do is they apply, and you can see I have an entire schematic here. I did not draw that. I got it off the web because there's geekier people than me on the web. You can see what happens is it shoots plasma out through these coils, hypothetically speaking, of course, and then pushes that plasma out and directs it using these coils here. So it can only apply a certain amount of force. So if you want the spaceship to go faster, you have to apply it over a larger period of time. That's the only way you can change your impulse. Now, that's assuming that you're keeping it at the same force level. So you could either change the force, or you could change the time, or you could change both. And so that's how they steer things, I guess. And NASA uses the same thing with ion engines. Same kind of thing. In fact, they have a plasma that shoots out through coils and then is directed through more coils that pushes rockets once they're in space. Okay, that's it for today. If you have any questions, please let me know. Again, we're going to use impulse when we talk about collisions, so make sure you got that down. All right, take care.